So let's discuss some ideal gas properties. Okay. So one of the things that we're going to, so the equation for the ideal gas is P times V is equal to R, which has to do with the amount of gas you have in terms of some units called mole. I'm not going to go into that, but R is some constant that you go out and measure, right? So the first type of change of an ideal gas that we are going to be discussing is the isothermal expansion. Okay, so what is isothermal expansion? It means that expansion at constant temperature. So if you take an ideal gas and you start expanding it, what will happen is that its temperature will tend to fall. But if you attach it to a reservoir, which is quite large reservoir heat, which has a constant temperature, then you can, as you slowly expand the gas, you can actually keep the temperature of your ideal gas constant. Okay. So as a result, what will happen is that as you expand it, because it'll tend to, if you were to like quickly, expand it, its temperature would tend to fall. But since you're keeping it at a constant temperature, that means that heat from outside has to flow in, right? Okay, so isothermal expansion means that you are not changing the temperature. So delta of T is going to be 0. Okay. So your change in internal energy this is going to be 0. So that means that your the work that you are going to do will be balanced by the heat that is coming into the system, right? This is exactly what we were discussing qualitatively.
Sir, that equation of this du, it kind of doesn't match with the first one that you wrote, I think. Could you, yeah. So there was another term, which was a dv multiplied by another thing.
Hang on. Which is so which equation are you saying?
The first equation du. I mean,
the du is CV dt.
No. Du is du dt plus du dv dv, and then yeah. Then we said that du dt when v is constant is cv, and this term does vanishes, but the second term I don't know whether it would vanish.
So this is essentially we are using the definition of CV here.
Oh, okay.
We are using this thing. Okay, we are using this. Okay.
So could you just scroll a little upwards so I can verify?
Sure.
Yeah, so a little upwards.
Yeah.
A little upwards. The first du when the du first arrived, a little upwards. Yeah. Sure. So the first term is actually CV according to our definition, right? So since dt is 0, so it vanishes. So what about the second term? Are we sure that it would vanish as well, as we're now saying that to 0?
Right. So you're saying that
the volume is held fixed in the definition of CV?
Yeah. The volume is just 1 second, okay?
If I'm not mistaken, the internal energy does not depend on volume. Isn't that why that one vanishes only for an ideal gas?
Sorry, the internal energy doesn't.
Doesn't
No,
depend on for an ideal gas.
Can I know what he asked?
No, what Nahi is asking is that why is it that I'm using du by dt? Why am I not using the second term? So what Nahi is saying is that we are changing. What happens to this term, right? That's what you're saying, right, Nahi?
Yes, sir.
Yeah. I think there's a good reason. Let me just think a little bit. Okay, just hang on 1 second, okay? So we are looking at isothermal process.
So for an ideal gas, I think it might be true to, leave the second term because the energy is generally something times kBT. So since the temperature doesn't change.
Yeah, I think that's basically, that might be the.
I see.
Yeah. I think that's it. Right. Yeah. Sorry.
Okay. So yeah. I should need a more convoluted reasoning for.
So who was it who suggested it the first time?
I did.
Okay, Saif. Yeah, Saif. I think you guys are right, but let me look at it and I'll get back to you in the next class. Okay.
Okay, sir.
But I think that's it. Yeah. For the ideal gas, because it's some, 1/3, 2/3 of 3/2 of kBT and something like this, right? So, yeah. All right. Well, thank you. So we have. Okay, right. So that means that the change in, say, the heat or the heat absorbed is going to be, say, dq, and that'll be minus of d of w, and that's going to be p of d of v, and this goes from v1 to v2. And for the ideal gas, it's v1, v2, it's RT by v of d of v, and therefore this is going to be RT log of v2 over v1, right? So we see that if v2 is greater than v1, delta Q is going to be positive, right? So All right, so the internal energy has stayed the same, but the volume has gone up. And so, as a result, and the energy density, which is energy per unit volume, has gone down, and the pressure will go down as well. Okay. So this is known as isothermal expansion, or isothermal. The other way would be like a compression, and then there is another type called adiabatic expansion, which is also important. Okay. So adiabatic expansion is when the gas is enclosed in an adiabatic enclosure, which means that there is no heat that can go in or out, and then work is done on it. Then then D of Q is 0. Then the change in the internal energy is going to be just given by D of W. So D of U is CV of dt, and D of W is minus P of dV. And therefore, what we can say is that, C of V, D of T is minus P of D of V, but P is RT by V. And so if you integrate this equation, we get log of T2 over T1 equal to minus R by CV log of V2 by V1. And also for the ideal gas, you can show that C of P is equal to C of V plus R. This is actually not very hard to show. And maybe I'll give it as a tutorial problem. And if you call gamma the ratio of CP and CV, which is 1 plus R divided by CV, then from this equation, if you eliminate R over CV, then you get log of T2 by T1 equals to 1 minus gamma log of V2 by V1. And then you can use the relationship between T and V, and so this basically tells you that T times V, gamma minus 1 is some constant. And you can express this in terms of P and V. And if you do that, then P times V to the power gamma is some constant. Okay. So these curves are known as so for every constant value, you can find a relationship between P and V, and those are known as Adiabats. Okay, so if I now plot the isotherms and the adiabats on the PV diagram for an ideal gas, it looks something like this. So let me, so the isotherms are something like this. And the adiabats are something like this. Okay, so these are the isotherms. So on an isotherm, the temperature is constant, and on the adiabats, something else is constant. Okay, so there is also okay. So any questions so far? So we've been just introducing some concepts so that it can facilitate the discussion of the second law.
Sir, I just would like to have a clarification on the signs. Like, for example, if we do work on the system, we say it's positive work, is it?
Yes.
And then if the system absorbs heat, we say that, dq is positive.
Yeah.
Oh, okay, sir. Thank you.
Yeah, I mean, no, sorry. When you're doing work on the system, you are that means that there is that, yeah, it has to be negative, right? Because otherwise your internal energy is going to be decreasing.
Okay.
Yeah, I always find this science a bit confusing.
Yeah, many people use many things.
Yeah, I mean, all right, so yeah, let's come back to that. Maybe we can discuss those things in more detail in the tutorial.